talking about the central limit theorem and sampling distributions in the context of categorical data. So with categorical data, we're going to be looking at the proportion of observations that fall in a particular category. We know that this is going to vary from sample to sample, so we had our sampling distribution result here. We saw that p hat was our notation for the sample proportion, and those are going to vary according to normal distribution, so n gave us that bell curve. And then we had fantastic news that even though different samples give us different results, they're going to be centered at p, the proportion for the whole population. And then the second term here gives us the variability, how much we expect our sample proportion, or p hat, to change or be different from sample to sample. Of course, we had a sample size criteria for this to apply. So let's check this out in context of our example of the number of accidents caused by people being on their cell phones when driving. So 2 parts to the question. First, we're looking to find the sampling distribution for the proportion. And after we do all that hard work, we're going to just verify that we actually can do that the result does apply. So when we're asked for the sampling distribution of the proportion, first thing we need to do is say what statistic we're talking about. They tell us right there in plain English, we're talking about proportions. Okay, so I'm going to write down p hat because that's the proportion symbol for the proportion of my data. We know this is going to vary from sample to sample, so I'm going to use this little tilde again to say my different sample proportions can be modeled by. N, we're going to assume that the result applies for right now, so they'll have this bell curve, and they should be centered at the value for the entire population. And we were given in the problem that p, the proportion for the whole population, was 0.28. We also want to know how much we can expect these different sample proportions, or p hats, to vary from sample to sample. So that was our 0.28, or p, times 1 minus p, over the sample size. And here we're talking about a sample size of 200. Okay, all of that is under 1 square root. So this is a complete answer to the first part of the problem of what is the sampling distribution. You need to include all of that. Say what statistic you're talking about and give the shape, the center, and then the spread. Now, I like to find the value of the standard error to use later on. So standard error p hat, not necessarily required right now, but just to have handy for later. If you do work that out, you should get 0.0317. Try it on your calculator and make sure you've got the order of operations correct. All right, so there's our sampling distribution for the proportion. What does p hat look like when I collect it for lots of different data sets? The second part of the question is just asking us to make sure that what we did was valid. Do I have a decent enough sample size to use that result? So let's just check that real quick. And we need both criteria to be true. So n times p in our particular problem, I've got a sample of 200 accidents. My probability of success, which oddly in this case means the accident was due to being on your phone, is 0.28. If you work that out, you get 56, and sure, that's at least 10. All right. Then the second part of this is the number of failures that are expected is also at least 10. So we've got 200 times 1 minus p. That should give you 144, which is very much over 10. So we're good here. So we could say our central limit theorem does indeed apply. Okay, so how does this help us in a particular problem? Let's flip over to the next page. Let's move to page 60 and check this out. So this particular question is asking us, What's the probability a random sample of 200? All right, so fantastic. We know what a random sample of 200 looks like. We just wrote it down on the previous page. Contains at least 60 that were due to cell phone usage. All right, so I'm going to start off by writing this problem in probability notation. So it wants to know, find the probability, so I'm going to use that P, that X, the number of accidents caused by cell phone usage, is at least 60. All right, this is a really important piece here. We're talking about proportions. 60 is not a proportion, it's a raw count. So I need to reword this question. The probability that X, the number of accidents, is at least 60, that's equivalent to the probability that P hat, the proportion of my sample, is at least 60 out of 200. So I'm just reformatting my question from raw counts to sample proportions because we worked really hard to say, to find out what the distribution of sample proportions is. Okay, so the really, really important part we just mentioned was that the p-hats follow a normal distribution, this bell curve. We know how to handle normal distributions. Our next step, we're going to take our normal distribution and convert it to that standard unitless z-score case. So my p-hat is going to change to z. Make sure you're careful of that. I'm converting it to z-scores, our standard normal case, is at least, and then remember your z-score formula we've had before. Z is our observation minus the mean over the standard deviation. All right, so same formula. The observation we're interested in is 30% of accidents caused by cell phone usage. What's the mean of the proportions? What was the center of that bell curve? If you flip back to the previous page, we said that was 0.28. And then what's the variability? What's the standard deviation? How much do these p-hats vary by? And we had that on the previous page as well. The standard error of p-hats, or the variability, was the 0.0317. Okay, if you work that out, that should give you a z-score of, let's see, 0.6309. Double check me, make sure we both have all our order of operations correct. Now we're totally good to go. You guys know how to find area under a standard normal curve. That's going to be normal CDF on our calculator. And I want the area above this z-score, so my lower value is going to be that z-score itself. And the upper value is going to be your favorite big number for positive infinity. If you work that out, you should get 0.2643. All right, that concludes this second video. We'll have one more video on sampling distributions of the proportion. But before we do that, I'd like you guys to try the remaining questions on this page. Then watch the third video to double check your work.